Hi everyone, we're Team 29, Deep Reinforcement Learning, Humanoid Robot Simulation. I'm Maggie Chong.
Hi, this is Tianze Ran.
Hi, I'm Gurman Singh.
Hello, this is Eric Wong.
Hello, this is Eamon Brake.
Our project objective is to apply the accumulation of problem-solving skills, game-based processes, and technical knowledge to research and gain a deeper understanding of deep reinforcement learning. In doing so, we took the time to learn what we can with this topic. It is a relatively new topic among machine learning and artificial intelligence. Our goal is to create an environment where a model can simulate real-life actions. We try to accomplish this goal by either modifying the models to replicate the action or conducting a simulation that makes the agents walk, which is our final product. With that, we researched and discovered a wide variety of reinforcement learning tools and libraries like GYM, Multi-Agent GYM, RoboSimo, Tensho, and more. We were able to learn and find commonalities and differences that made each one stand out. We'll talk about our experiences from the most important resources used in this presentation. Some of the common components to this project was MuJoCo and TensorFlow with the earlier libraries that we had. The ones in the darker green circles are the ones used in our final product.
Here are the fundamental elements we learned for reinforcement learning, those being reward signal, policy, model, and value functions. In each time step, the agent receives the calculated value called a reward from the environment, and it takes action in a given time frame based on the policy implemented. We conducted research in greater breadth and depth about the type of policies that are used in research today. Here's a variety of different RL algorithms that we've researched. This project ultimately produces agents capable of driving humanoid motor function using deep deterministic policy gradient, proximal policy optimization, and twin-layer DDPG with a Tensho framework, some of which produce a stable walk.
MuJoCo is a physics engine that facilitates research and development in robotics, biomechanics, graphics and animation, as well as machine learning. It works well with RL applications due to the possibilities such as XML parsing, model compilation, interactive simulation, model visualization, and its flexibility in Python and C++. These models can represent complex dynamical systems with a wide range of features and model elements, which are easy to modify for the purposes needed.
To create these custom XML models, we follow MuJoCo's custom format, or MJCF. We developed our custom models from MuJoCo's humanoid, four-legged ant, and two-legged cheetah models. The modeling process included creating new body part shapes, adding or removing existing appendages, and modifying a joint's direction and range of motion. Here's a list of all the custom models we produced. This is an example of an 8-legged ant with 4 legs up and 4 legs down in the rendering environment for the two versions of MuJoCo we used. The right is MuJoCo 150 and the left is 200. By dragging and dropping XML files in either of these environments, we would determine if a model was correctly written and thus be able to make rapid design changes to reach the desired result. Here is an example comparison of two simulations that we performed between the 4-legged ant model from MuJoCo and our own custom 6-legged ant model. We ran a script that creates an environment for the XML model. This produces an agent for each ant model, which chooses some random action and yields some reward which is fed back into the agent. When a failure condition is met, marking the current episode as complete, a new episode is started and the process repeats. Tianze will talk more about how this is done using OpenAI GYM next.
OpenAI GYM was a toolkit made for developing and comparing reinforcement learning algorithms. We use the GYM to test the custom models by having the agent controlling the model perform random actions to try to walk. GYM also allows users to define a multi-agent environment, which is packaged into multi-agent computation, shown by this example of a two-agent environment like Sumo. However, the package contained errors known to the contributors that prevented the rendering of these environments. Thus, we move on to Tensho. Tensho is a reinforcement learning platform designed to be API-friendly. It contains examples and input instructions, resulting in flexibility for training the model. It already has policies to experiment on each one. These three code snippets show the different parameters in our test script. In the image on the left side, we specify different reward thresholds for different tasks. The middle image shows a number of parameters for command line arguments. In particular, actor learning rate, gamma, etc. represent the hyperparameters of a given policy, and epoch is for specifying the maximum number of epochs to execute even if the reward threshold is not met. In the right image, the code snippet is run when the result needs to be visualized, and an episode determines the number of episodes to render using MuJoCo. Here are some examples of the script running using different epochs and reward thresholds. Best result demonstrates the mean and range of all rewards for the best epoch in the whole process, and the best reward indicates the highest stepwise reward in one epoch. The first example stops at epoch 19, where the best reward barely passes the specified reward threshold 160. Similarly, the second example stops at epoch 52, and the third at epoch 128 with higher reward thresholds. Gurman will talk about the policies involved next.
We originally ran the deep deterministic policy gradient algorithm at a starting threshold of 300 to quickly train and see the results of basic simulations with a humanoid model learning how to walk with DDPG reinforcement. As you can see, the model is making some minimal efforts to maintain balance. The PPO and TD3 policies had similar results with slightly more arm movements and combined arm and chest movements respectively. After setting the reward threshold and epochs allowed for training to high levels, we were able to run simulations over several days that resulted in a model able to walk in a stable manner at a relatively quick pace. As you can see, the model holds its arms close to its body and locks its hips in to form a stable walking movement. We tried using proximal policy optimization to teach the humanoid model how to walk, but were unable to train it to reach higher reward thresholds despite increasing simulation time and duration. This algorithm got stuck every time we ran simulations and could not teach the robot how to walk. Further modifications would need to be implemented in order to do so.
Finally, we have twin-layer DDPG, which we anticipated to perform better in terms of walking distance, speed, and other factors. This is because TD3 uses two deep Q networks found in DDPG, which should solve overestimation as more noise resistant. Trials 1 and 2 trained faster for similar reward thresholds, but both humanoids only made a few steps in each episode, as you can see here. The third trial failed to render and reach a reward threshold 5,000 after 1,000 epics. Overall, this project has served as a great learning experience for working with various RL platforms with the MuJoCo physics engine. We were able to get a good sense of the amount of knowledge and research it takes to implement RL policies and execute simulations using multiple packages in concurrence. Thank you for your time, and have a great day.